So, have fun.
Michi. Is there a pointer here?
Yes.
All right, so it's a pleasure for me to be here. My name is Zyad Shehata, and I'm really happy to kick off the Entropy of Entanglement. So, Sebastian already talked about the idea of knowing of entropy, but I'll take it in another angle, and maybe to let you see something that you can measure in your lifetime. So, for example, these not eggs and cartoons, yeah, they're really like this. Yeah, they're atoms, they are confined like eggs in a cartoon, and you really see how we can use that to manipulate and understand how can we measure entanglement entropy. So my outline will go like this. First, I would love just a little bit of something you already know, that was non-classical correlations. I would like to also introduce a new definition of how can we write down a wave function using something called Schmidt decomposition. And this is the heart of the topic, is the entanglement entropy and how we can understand entropy in quantum systems, and how can we detect such entanglement and measure them. And well, for our preferable system, it's a quantum many-body system, and I will talk more about this. And finally, the entanglement distillation, and how can we use protocols to design more concentration of entangled states. And then finally, I will close with an algorithm. Well, the basic question, why is quantum mechanics bizarre? The answer is entanglement. Why we cannot simulate quantum physics in decent supercomputers? The answer is entanglement. But the third question is, why there is really a hot argument between theorists and exponentials now for the locality and non-locality principles, is because of entanglement. So the wave function that we can write down a complete wave function in the Hilbert space as a superposition of different spatial configurations of, let's say, spins or rise photons. This is going to be summed over a whole coefficients raised to n. That's why this complicates the Hilbert space. And this, what we really cannot simulate such entanglement correlations, because those atoms or photons or states or base functions, they are really entangled. There are some correlations. This is the non-classical scenario that I'm going to explain now. And David Hilbert, of course, a German physicist, German mathematicians are really up to the way right now. And well, if you do have conversations between Alice and Bob, Alice would say, okay, we need to have access to such entangled quantum many-body from wave function. And Bob will say this is really too complicated. That's why if you want to simulate all the spins, like, okay, you want to simulate entangled states in computers that would need the memory of your computer will be in the size of the universe. The size of your memory is actually the size of the universe, because you need, like, if you need 300 spins, which are still like, well, not good, a good number of spins, you need well, memory that exceeds the photons of the entire universe. It's really hot and really a big superpower that you need to simulate such states. So for 2 raised to the state, so 2 to the power n, that's exactly what happens here. So this is taken from Los Alamos. And well, first part of the talk is what's really non-classical correlations. So well, you already know you have entangled state, you have something that's not factorizable, non-separable state here. So you can see that there are some entangled, some non-classical correlation called entanglement here, but there is no entanglement here because you can separate a wave function, as you already know. And this leads us to talk more about the very fashionable entangled states, the Bell-Pierce. This is just very quick. Well, the entanglement from T up to this moment is that we can simulate, well, we can study systems. And those systems can be Trapp-Ion systems, as we already mentioned last talk. This can be neutral atoms, cold atoms, and optical lattices. I think you missed this, but this is a very fashionable way to design special purpose quantum computers. And also something like the superconducting circuits from different papers. Just I would like to mention that you can also have superconducting Josephson oscillations or Josephson functions. And also in an NV synthesis in diamond, there's also good progress in such arena. And those are all the systems. Those are all really the platforms. You have superconducting qubits, you have ultra-cool atoms and optical lattices, you have polar molecules, trapped ion system, and so on. So we move now to express another way of how can we write down a wave function using a good way of that leads back to Ernest Schmidt. He's also German. Well, this is the basic phi, so we can write down the phi as a sum for all for two systems. Let's say that's a bipartite system, and we can sum for all the let's say the coefficients, and B is called the Schmidt coefficient or Schmidt factor. How can we prove that? Just very quickly, if psi is a normal wave function, we can write down the wave function as a sum for all coefficients C. And if you take the square root of C, it gives you the probability of such a state. But we can say that, well, we can say that C and M with M for the subsystem B, it's equivalent to M tilde B, okay? By the way, A and B are the bipartite systems that they are not restricted to be orthonormal. They can be orthonormal. There is no just restriction on this, but we just suppose it's random. And if you want to write down or spectrally decompose and write a reduced density matrix for subsystem A, it can be the projector for the subsystem A. And you sum for all the coefficients of the Schmidt. Now, there is the Schmidt coefficient square, which is the eigenvalue, which is also called a global factor. And of course, from quantum information, we can trace the system B, and we can obtain, after some simple algebraic format, you can reach such overlap between the system for each system B and for system A, tensor product here for system A, and you separate the two systems away from each other. And by some conventions related to just separate the M and N inner product state for subsystem B, you can end up using this relation, which confers a delta function, an inner product state between two systems now related to the subsystem B, which is already part of the Hubble space. So we just need to normalize the eigenbasis of B. So we just already here introduce 1 over dn to normalize eigenbasis. And then after just a simple algebra, you can already end up with the relation of, as I said before, the Schmidt decomposition relation here, which you sum over all Schmidt coefficient raised to subscript n. And we need to ask ourselves, does Schmidt decomposition have uniqueness? Well, let's see. Let's propose well, very fashionable EPR pair. So this is an EPR pair. If you look at the EPR pair, for example, you see that the coefficient, the Schmidt coefficient, is actually the same for two Schmidt vectors. This is called degrees of freedom related to the global. So it's called the global degrees of freedoms, and these are called the local degrees of freedoms for the Schmidt decomposition. So we see that 1 over square root n is non-distinct. So we call it Schmidt coefficient. Non-distinctness called degeneracy because you have two the same probability for each Schmidt vector, which already well-defined eigenvalues or singular values. And this leads us to say that, well, the Schmidt vector, as we propose it, that's non-unique. So the Schmidt vector is non-unique because of the non-distinctiveness of the Schmidt coefficient. If you break the degeneracy, you get unique bases, but up to phase, and this phase can oscillate here. You can put a phase, and this phase can exist here. If you put it beside the coefficient, there will be some problems because the phase might be complex. Of course, it's complex, so it will affect the Schmidt coefficient, which has to be real. That's why you will just rotate it around here. You will see that if you break the degeneracy really in such a Schmidt decomposition wave function, you can break the degeneracy. So let's write down again a trace of B for such rho. So we can trace system A with a projector phi, and you end up simply by this definition, which I would like just to focus on dn squared because it's very important to characterize entanglement. So the Tn square is the eigenvalues, which is a Schmidt coefficient or Schmidt factor square. And this leads us to say, or to define that the number of non-eigenvalues, non-zero eigenvalues, this is called a Schmidt rank or Schmidt number. And from such definition, we can just say that if you do have one Schmidt number, it's a simple state. This is how we can characterize theoretically or logically entanglement from such Schmidt decomposition wave function. That you would say it's a pure subsistence because you have a global system which is pure, and also the pure subsistence that exists if you do have one Schmidt number. It's a separate state. But if you do have more than one, that is different. Now we will move to be more entangled states and more mixedness related entropy. So now it comes to the entropy. We move to write down the entropy for the state, the phenomenon entropy. So it's a trace of the rho and rho. And the entanglement, or the entropy of entanglement, this is the entropy for both subsystems. We would use density matrix for A and B, right? That's why if you want to trace entanglement in such, let's say, an Wari system, you rather look at the pure, you rather not to look at the pure global system, but you look at the constituents of the system, which might not be pure. That's why you have to make sure that you look at the, that you have to make sure that there is no mixedness for the subsystems. That's why there are a lot of studies have been done to try to measure entanglement, which, well, I'd say that this study is the heart of measuring entanglement entropy. You can see here a product state, you can separate the system as tensor product, it's not entangled, it's entangled, but here it's more entangled state, you have mixedness for the subsystem. So an example of that, we can work for this example as spin up and down, or let's say horizontal or horizontal, vertical polarizations of light with weighted factors for the probability. If you rewrite or decompose this wave function, this density matrix for A, you can read it like this for below, and we can work also we can proceed to write the or express the entropy of entanglement for such wave function, and this is exactly mapping from the upper definition. This is the entropy of entanglement. We would like to plot the entropy of entanglement and to see that if you have the P, so we can see that if P is 0, all right, you have no entanglement. There's a product state. But if P is 1/2, you have maximally entangled state. This is maximally entangled point. But it's still no logic or multi-route. The problem is that we want to simulate, we want to see something in our lifetime. So I just quoted very important, let's say, quote. I got it from the other paper here, is 2012, saying that there is a big challenge, an intellectual challenge if you have many particles. In real life, you don't have many atoms, you have many wave functions. And we want to detect entanglement between one wave, let's say, basis point, another basis point, but you have many constituents inside the system. And that's why many efforts have been devoted into measuring entanglement entropy or detecting entanglement per se. For example, one of the studies pioneered by Anton Zillinger in Austria, so the GHZ state is called Greenberger, Horner, Zillinger. It's a very fashionable three-particle entanglement state. Three-particle entanglement. You can do that by atoms, ions, photons, whatever. But you do it. Well, this is very well manifested in the context of quantum optics. This is three-particle entanglement. This comes to the violation of Bell inequalities, because here you have no locality principles here. And what happens next is that some people would like to characterize entanglement by something called entanglement witness, a witness operator, that you can take all the non-locality principle to map it into observable. But still, I would say that the witness of entanglement has not been motivated by, let's say, rigorous experiments. That's why we can rely on the principle of tomography-independent measurements, and we can shift this to the area of quantum many-body systems, because you have eternal particles, and you can work with them, and let's see how we can do that for the context of eternal quantum many-body systems, or interference. So the quantum many-body entanglements looks like good title to pose. And the real thing is that we are trying to search for something that's beyond breaking the degeneracy. So we are not going to talk about integer quantum Hall effect, fractional quantum Hall effect, topological insulators, and something like this. Because in condensed matter physics, you cannot, well, at this moment, you cannot detect entanglement. It's a big problem. It's a big problem in condensed matter physics to simulate entanglement states. That's why we can look at synthetic quantum matter as quantum simulators. And what are really those quantum simulators? This is the cartoon that I showed you. That you can superimpose laser beams in 3 dimensions to create something called optical lattices. And you can freeze the atomic degrees of freedoms into a phase called the Bose-Einstein condensate phase. What I want just to show in this slide, you don't have to know all the details, but I want to show that this is the Bose-Einstein condensate phase with large particle number fluctuations that you already can find using the optical interference of light. And this is another phase called a multi-insulator phase, and you can go from a BEC, Bose-Einstein condensate, to a multi-insulator phase using some techniques. But why is it connected to the entanglement? Because you already have here large entanglement properties existing in a BEC. So the BEC, we can talk more about this, but the Hamiltonian basically of such system that you have, it's called the Bose-Hubbard model, because they are bosonic atoms. You confine, or you isolate, or you trap bosonic atoms. And the Hamiltonian is that you sum for all the kinetic, this is J, it's called kinetic term, so let's make it simple. An atom will move from here to there, a ton. This is J. For atoms existing in 2 lattice sites, they would interact, repulsively interact. This is connected to the U. So here you have kinetic term, you have potential term, and this is a term that's not really that important in the context here, which is a chemical potential related to the atoms. We can talk more about this afterwards, but this is not okay. So what happens is that to measure entanglement entropy in quantum body system, that you take, let's say, something from this slide, we take BEC and superfluids, called superfluidic state, and this is a bad insulating state. If you have 1 atom per lattice site, it's called multi-insulator phase, and you try to cut the system because you want to study subsystems. Now, if you cut the system, you see that the wave function can be a separable state, can be a factorizable state, which is a multi-insulator phase, because there is no kind of entanglement that happens here. Right? Because such atoms just exist all the lattice sites. But if you do have large particle number fluctuations, which means that the phase can be well defined, then you have the non-separable state. This is an entanglement state. This is how we can really synthesize entanglement states. And they are really precious because they last for couples of milliseconds or something. Then you can write down also the spectral, reduced density matrix as a tensor product for such projector. It's a projector state for, let's say, for subsystem A. And if you trace A and B away from each other, you'll ask yourself, when you trace or cut the system, do you increase mixedness or not? If you increase mixedness, now you can have to entangle. But the main thing that I really like to say, because Sebastian, you already talked about the phenomenal entropy to measure entanglement, but this is really inaccessible to experiments because it's very hard to simulate. That's why even if you look at the Renine, it's called second order Renine entanglement entropy, you will see that even this is non-observable. There are no observable here because the observable should be something traced linear. But this is traced rho A squared. And this is truly a big problem yet. But what I want to say that phenomenal entropy is not accessible to experiments to simulate. But how can we solve also the problem of the trace of A squared? I will let you know now. What you basically measure in such experiments is the quantum purity. So you will want to make sure that the trace A squared is equal to 1. It's a product state. Okay. And if trace A squared is less than 1, you have entanglement. Let's see how we can solve the problem of this nonlinearity. So the proposition, how could we manifest Renine entanglement entropy using the Holm-Mandel effect? Because Holm-Mandel from quantum optics, if you don't know what, you have 2 photons, let's say one photon and one photon, you send the two photons into a beam splitter. And then if the distance is well tuned, you detect two photons on one side or two photons on the other side. You never have coincidence clicks. One photon on the detector, one photon on the detector. It doesn't happen. This is the idea of homomanda. So what happens in the experiment here with homomanda interferometry, you have two input beams here, two photons for example. They will come together at one port, or they will come together at another port, but they never come separately. You have to tune the distance, otherwise you lose the control over this. This was one of the pioneering experiments to begin quantum optics by Orlando. And now we can take the idea to detect entanglement, because what we do in detecting entanglement is the same that you have to interfere to quantum systems, or many body quantum systems. And you measure something that related to the average particle number parity. I know you see it now in the notes. So from parity to purity. So from parity, the particles, to quantum purity, to measure entanglement. And the study is done by Marcus Bryan at Harvard Quantum Optics Group in 2013. Sorry. 2015 by Marcus Bryan. So what happens is the following: that you do have two copies, you interfere them, and they will come together. There is no odd particles, because as I said, we measure the average particle number, which doesn't have odd result. So the odd is discovered. And you just have kind of even distribution, and what happens is that the same, you take the wave functions, that's why you can map it to the average parity, and now we can really say or claim that we solved the problem of nonlinearity because you have two systems that interfere now. Now we can be, there's no problem for such purity, because here you can measure the purity very well defined. But still, I give you also a challenge that, well, let's see how it works. Is the BEC, the Bose-Einstein constant, with large number particle fluctuations, or particle number fluctuations, or variance. But here you don't have any fluctuations in the number of states. So what happens is that you will cut the system. Okay? Now we cut the system, and you will do homomanda interference. You will see that at the globally, it's a pure state. And locally, it's also a pure state. Here you have even for the two sides, and you have also even over locally. So globally, it's even parity, and also for the local degrees of freedom, it's also even. That's why it's disentangled. As I said, now you can map also. If you detect something like this, you say there is no entanglement. But for what's more interesting is that you do have for BEC, if you do a mixedness of the system, you do homomanda interference, you will see that, well, there is some, globally it's a pure state, but sub-global, locally, it's non-pure state, because you have fluctuations now for odd, even. Now you can see that here it's odd, locally odd, but globally even, here locally odd, globally even. This is how you can detect entanglement. And the signals will go like this. So you have here no entanglement. You begin from a multi-insulator phase. You increase your entanglement because how you have mixedness here in the state. Two atoms to the lattice side. Now you can oscillate back and forth. This is called the quenching. When you go from a phase in a multi-insulator phase to BEC, you quench the system. Okay, this is called quenching. It's a very important experiment. And also another thing that you can measure in my entanglement entropy, because the entanglement will increase once you shift from multi-insulator phase to superfluid phase, and here you just decrease the on-site interaction, which means that you increase the kinetic term. If you increase the kinetic term, you go to a BEC. That's why you can really have entanglement in the system. This can be well. Okay. So now we already finished up with the entanglement entropy, but we will move to how we can use entanglement to concentrate a signal. Okay. We do have Alice and Bob. Okay, they want to do some security protocols, but they have a problem. Is that when they prepare entangled state, they always lose control over the strength of the entangled pair, or the entanglement system that we have. Well, the weak entanglement. And if you even put repeaters in between, you also have problems. You also weaken the signal. Even if you increase it at some point, you also have low quality waves. That's why it's called distillation. It's entanglement distillation because you take it from the idea of alcohol and water, everything is mixed. So you want to evaporate the things that you don't need, and you put the things that you really need. Eventually, you concentrate the signal like ethanol and alcohol, water, and propylene, whatever. This is why it's called entanglement concentration or entanglement distillation. The protocol goes as the following. We manifest the CNOT gate. The CNOT gate is, well, we know it because if you don't have, well, from even classically, but it's a quantum gate that if you have a 0 at the beginning, you don't change the output. But if you have 1, you change also the output of the second bit. So you can really claim that CNOT gate is correlating the two copies of the quantum systems. They share a source, so the protocol goes as the following. They share two entangled pairs. One of them is called the source, if we like to increase the entanglement, and the other one is called the target. And this will we use it in order to increase the entanglement of the source pair. So what happens is that they do measure, they do perform a CNOT operation. When they perform a CNOT operation, as you see, they collapse the target pair, and if you collapse the target pair, you can also look at the source pair, what happens, and then they can communicate with each other using classical communication channel. And by the way, I didn't tell you that they can also share a very good signal, a very good quantum state, which is a bell pair. So they can share a bell pair, and you can look at the outcome. But there is also a problem. There is also a problem. The problem is that they can have something like, well, some errors that happen, and then they can include in their protocol some errors like an orthogonal state like 0, 1, which is orthogonal to the bell pair, which is also a big problem. But we can also manipulate this using this the protocol, and the rigorous protocol will go like this. Now you have a source and a target and a phi's, and you do perform CNOT local operations on the source and the target, and then you look at the outcome. If you do have the source and the target without errors, you have the same state. You don't have a problem. But if you have errors in the target, and then this will correspond also with those errors in the source, you get a different state, like this. If you want to make sure that it works, just CNOT operation on the states. But another scenario that if we do have errors in the source, you get output. But if you do have both errors in the source and target, you get another signal. So if you look that you want to measure, for example, a 1-1 state for two subsystems, for two A2 and B2, you look at here that this is the only solution to get maximally entangled state if you don't have errors in the source and the target. That's why they will call each other, and you want to make sure that over kind of probability distribution over the all outcomes, you can manifest the idea of to maximally entangle the states, and you can make sure that you already don't have a weak signal or a weak output, otherwise you discard the outputs, you discard the quantum states. But there's also a challenge, I took it here. The challenge that if you get a signal and you want to see the fidelity, how they are really close to the main input, to the main copies of their states, there is a problem or a trade-off problem between the fidelity and between the probability to get the same desired outputs. That's why I already denoted here. I already denoted here that there is inverse proportionality between the probability of getting the same outcome repetitively, because you will do this protocol many times, and the fidelity and how good the state is. Otherwise, you discover the state. So the outlook. So now we're done with this. Very simply, that entanglement are really unique and precious. If you prepare entanglement, you have to make sure it's alive. Otherwise, you need more effort to sensitize it. And Schmidt decomposition is a useful way to characterize entanglement in the language of quantum information. And many-body entanglement is also of paramount importance if you want to see something in your lifetime. Okay. And there's also a number of particle-limited correlations, as I told you. That now we just did all the scenarios and just fixed, let's say, limited number of particles. But if you increase more the particles, you never, until this point, you never measure correlations. There's a big problem here that And I even don't believe it would be accessible with more than 10 particles, because from the literature it's well known that if you have more than 10 particles, or more than 6, well, let's say from 8 particles, you have very weak correlations. You cannot do the experiment as I showed you. And another outlook is that we can use the CNOP operation, the CNOP gate, to correlate the states, and we can improve the security protocols by entanglement dispersion. And actually more to come. And with that, I'd like to thank you for your attention.
So, thanks a lot. And first, to the audience, are there any questions left from our answers throughout the talk? Anyone? Yes.
So I wanted to understand the statement a little better that you made, that we cannot measure entanglement entropy, or we cannot measure entanglement. So I understand the first statement, like probably entanglement entropy is really hard to measure in an experiment, that I can imagine. But the second one, that we don't, it's hard to see entanglement. I thought that was the point of these Bell inequality violation experiments, that precisely you do see entanglement. Maybe you can.
Okay, so I want to get back to maybe one of the slides that I want to say that, for example, to this slide and also the common one. The effort has been divided into many protocols. So you can measure entanglement using different ways. One of them is entropy, of course. But you can also measure entanglement using a witness operator. But it's more mathematical, and nobody tried to show an experiment, as I believe. But it's truly hard to do that for particles in general, for atoms, because there is always kind of itineracy in the system. So you have particles that are hopping from side to the other. That's why, as I said, the problem is that for also the good usefulness of quantum many-body interference, that you do already have manipulation to the system, because you can put just one particle per data site, and then you can trace how they would be correlated to another particle in a different site. Let's say here, for example. So it's an intellectual problem, because you can imagine that you just put one bosonic atom, one bosonic wave function in the lattice. It's a big challenge. That's why I said even if you increase the number of particles, there is a big problem, because there is always itineracy in the system. And you cannot map, let's say, 10 particles, because BEC of 10 particles is also a big challenge to synthesize in the lab from the experimental point of view. So measuring entanglement, measuring entropy otherwise, it's as I said, it's a big intellectual problem in the context of quantum interference for more than, let's say, more of that.
So the statement is somehow that we want to have many particles that are entangled in a complicated way, and we just say that to keep this under control somehow experimentally, that's a very complicated.
Yes. And also the lifetime of the state is so short. So we take the snapshot, and then you want to repeat the measurement again to cool down atoms to prepare the density matrix. Emmanuel Boch is doing this very well. He is not measuring entanglement, but Marcus Ryan, I see the paper that coming from the group of Ted Hensch, using the PhD period of Marcus Ryan and Emmanuel Boch, and Tilman Islinger also in Switzerland. But Emmanuel Boch is doing it very well, and he's also tracing that, but Marcus Ryan focuses more on the entropy of entanglement.
So I was wondering about the separation of the Bose-Einstein condensate. And the question is, how can you eventually prepare a matrix of nicely upper lattice from particles that are likely to condensate, which normally are every particle you can trap in optical lattices. So how do you avoid these problems?
Do you avoid the interference between the atoms? Or?
Yes.
So what happens is that you do have laser interference, laser cooling. First you laser cool the system,
Yes.
Depending if maybe you can use a converter cooling, but here what happens is that you interfere just the light, and you can make sure by interfering the light that the atoms are trapped. Okay, you begin with a circle fluid phase. It's supposed to understand constant phase as non-effective temperature, and there are always fluctuations in the particles. So what you want to avoid is that the particles will stay in the trap, and otherwise the particles that are unstable, they will be kicked out of the trap, which is a good thing, because you can condense all the atoms which are more stable enough into the system. Okay? And this is just using by laser interference. It's very beautiful experiment, and this is one of the most cited papers in physics, I would say. That's why you do have here, this is a Bose-Einstein condensate phase. You have a well-defined phase here for BEC, but you can also see that the phase here vanishes, because it's a Fock state. You don't have particle number fluctuations in the system. There is an uncertainty, anybody can use this, and there is an uncertainty between the particle number variance and the phase of the wave function. So this is related to the BEC mods. So for N, if you do have for BEC, then the phase is well defined. That's why you see here interference pattern. And it's a Gaussian probability distribution because it's a coherent matter rate. But in the multi-oscillator phase, it's a Fock state. And you can tune that by just a normal laser tool. That's it.
Okay, thanks. So, any further questions? Yes, please.
You mentioned this rainy entropy. So did I get this correctly? That this is so you also take the partial trace.
Yes.
And then you don't take the von Neumann entropy, but you just take the trace, the log of the trace of the square of this this thing. And the statement is this is another measure for entanglement.
Yes.
So and the statement is that when is the system entangled? If this is larger than 0?
Well, if the entropy itself is equal to 0, you don't have entanglement.
I see.
But if you have larger than 0, then there's more entropy in the system, you have entanglement. But I want to say that the second order in entropy, it's a complementary, we can say it's another picture, it's a complementary picture for entropy.
So this is what I wanted to ask. Is there some sort of, can we make some statement about the relationship between von Neumann entropy and this Rayleigh entropy? Are there some inequalities or something?
Yeah, well, I haven't thought about the theoretical relation, but what I just tried to understand that you simulated, or the quantum simulated the system for the atoms using Rayleigh entropy, because here you just have the trace of it's non-observable, but you have just a trace. If we go back to von Neumann entropy, for example, you can see that, it's a trace of rho and rho. So what you want to say, okay, how can we overlap the wave functions using this proposition of the Neumann? Because the density matrix is taking rho and rho, which is not linear as well. And there's a problem that even if you go to Rayleigh entropy, you will see that also the non-linearity issue, but they overcame the problem by just interference, by just quantum interference of the two wave functions. But you cannot do that for Rayleigh entropy, basically.
Okay.
So what does the second order mean? Second order Rayleigh entropy?
Well, the second order is this is just a suitable way to characterize the entanglement entropy, because there are more versions of Rayleigh entropy. The second order means that you take just a subscript 2, the general form, which I don't have the general form now, but this is just a kind of something like expanding the entropy into a second format, the second order.
So approximation.
Approximation, exactly. And this is the second order is for entropy, for entanglement entropy.
Concentration. You talked about entanglement concentration in the last part of your talk. So, since I'm not an expert in this topic, I just know sort of one. So I have some picture about what this is, and my picture was like you convert your entangled state into pairs of, into Bell states, or you convert Bell states, you use Bell states to build your entangled state. And typically you need, and then the question is how many Bell states do you need to build your entangled state? That's certainly a measure of how entangled your state is and vice versa. So your thing here is about quantum communication, and I didn't really understand what gets concentrated, what gets distilled.
Okay, so the answer for this second choice that you said, you use a bell pair to prepare entanglement concentration.
So that means Alice and Bob, they share a bell pair?
Yes, they share 2 copies of the bell pair for the source and the target, both.
They share what?
2 copies, because they have a source. This is a copy, and the target also. Yes, maybe we can move to this one. Here, yeah. This is 2 copies for the source, and 2 copies for the target. And what they normally do to perform a CMOP, to perform, yes, this is a CMOP operation. That you perform a CMOP over the 2 copies now of their target and source. And they wanted to use the target copy to make more correlations of the source. So the basic idea that you condense more, you put, let's say, more entangled states, you evaporate the less entangled states, and the remnants are just more entangled, good entangled states. Because they want to communicate, so they have to make sure that.
I see. I think now I get it. So this is actually very much related to what I was saying. Just I wasn't talking about Alice and Bob. I was just talking about some people. Just one person that is doing this in the lab. You don't have to be separated, but certainly it is useful to do this for communication. Thank you.
I guess every question got answered. Thanks again.